Lesson 61, box plots. We'll be able to construct a box plot. That's the pretty simple thing here today, is we're going to be able to construct a box plot. We're going to look at how to analyze box plots probably on Friday, but yeah, just the basics here is what is a box plot. Now, box plots were the last topic that I wanted to cover at the end of term 3, but I thought to myself, I don't want to rush them because I would like to have a whole double to teach them, just because they've got a little bit of stuff to do in them. So I thought, let's take our time. So before I jump into box plots, let's actually get a refresher from the very end of last term. What were we doing at the very end of last term? At the very end of last term, we were breaking down the main ideas of mean, median, mode, and range. I actually tried to compress a bunch of ideas into one lesson. Probably too many ideas into one. I think it was a double lesson. It was. No, it wasn't. I think I did this in a double lesson, and I think I kept the Friday free for just to go over some stuff. But yeah, we first talked about how do we organize data. We talked about 2 ways to organize data. The first is called just a simple dot plot. Dot plots are one of the easiest ones. Oh my god, if you get a dot plot in a test, you should be like, thank God, it's like 3 kind of marks. Because all you're going to do is put dots places. And then of course you can, and it looks like a histogram, so you can actually get questions like, oh, is this a symmetrical distribution or is this a skewed distribution? Some people, you can also get questions like, you know, how many people take 10 minutes or more to eat breakfast? So you could go, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 people because you can count them quite easily. And that's the simple dot plot. We then jumped from the dot plot to the slightly more complex stem and leaf plot. Now, the reason we like the stem and leaf plot is because the stem and leaf plot actually gives us an order to understanding the information. It's in groups of 5 or 10, and then you take the first digit away. So, for example, this number here is not 5, it's actually 25. You take the 2 and you put it in front of the 5. What's really good about it is because it's all organized, you can use this quite easily to find the median, you can use this quite easily to find the lower and upper quartiles, and so on and so forth. So these are a quick and easy way to organize information. You can also have back-to-back stem and leaf plots and so on, but we're not really looking at those in the moment. I think we're going to look at those later on in the next topic, I think. Don't quote me on that though. Stem and leaf plots can have more than one range. I did sort of point this out just as a quick heads up, because often I've seen this before where they go, okay, so this number here is 15 because it's 1, 5, so it's 15. And so all of these numbers are larger or equal to 5, and all of these numbers are smaller or less than 5. And so therefore we've got 10 to 14 here. And it's just because, like, if we were to have all of the numbers between 0 and 10, this would be a really long list. So instead of making a really long list, they split it up. You can also get an idea of the general shape of a distribution here. I can actually tell from this distribution that we've got a shape that looks like this, which I'm going to say, because it's easy to climb from a positive, this looks like it's positively skewed. Now, if you don't remember the positive negative skewed, that might be something worth looking back on. It's positively skewed because it's easy to climb from the positive. We did some, then we talked about the histogram. We've already talked about histogram back here. So yeah, jumping ahead, after we did that, we talked about something that you should have heard these terms used so many times before, probably in year 7, probably in year 8, maybe in year 9. Mean, median, mode, range, interquartile range. And what we decided, interquartile range is probably new, but the other ones are pretty old. And we went through what each of them were. We said, well, the mean is like the average. When you're looking for the average result, you add all the numbers and you divide them by each one. You sort of like trying to find the approximate middle number in a way, because the approximate center. But there is a problem, and the average is a really good way of figuring that out. But the average doesn't always work, because we talked about the median. We talked about Adjuville. We said in Adjuville there was one $10 million house, and so that kind of ruined the whole average, because it was like, oh, well, that made the average about 3 million. So then we said, well, the median is the middle number. It's the middle number of the set. And that actually means it's an actual number in this case, which made it very easy for us to sort of get an idea of, well, what is a good understanding of the house price in this particular region. So median, and sometimes as well, we like to use the score. And especially when you said test results are a really good way. If you've got one student that gets 1% and, brings the whole class's test average down to 67%, that's going to be really annoying. So that's why sometimes with test averages, and this also occurs when we look at like ATAR scores, by the way, FYI, we usually look for the median study score, not the average, the middle one, because that gives us an idea of roughly what the students are like. So yeah, the mean doesn't always make sense, so that's why we use the median. The median is the middle number, so if there's an odd amount of numbers, it's quite easy. You take these, there are 7 numbers here, so you go 7 plus 1 divided by 2 means 8 divided by 2, which is the 4th number. I always put the TH here, so do you remember that it's the 4th number, not the median is not 4, just because you do it like that. For an even amount, it's a bit harder. Obviously, for this one, there were 8 numbers. 8 plus 1 divided by 2 equals 9 divided by 2 equals 4.5 number. So you're looking for the number between the 4th and the 5th number. So you take those 2 numbers and you average them. 26 plus 30 divided by 2. And then what we did is we quickly we did the issue with having an ordered set. In this case, that set above is not ordered, so you can't do it. We talked about mode. Mode is the most common number. We sometimes don't refer to mode as like the most common value. Sometimes we'll refer to a modal interval or a modal class. And that's like saying, well, in this case, the modal class is 30 to 40. Because that's where most of our results occur. And then range. Range is the highest to the highest minus the smallest. So range is different. Range gives you an idea of spread. You think about mode gives you an idea, and median, these guys give you an idea of center. Where is the middle of the data? Even mode gives you an idea of center. Where is the middle of the data? Because it's like saying, well, where are most of our values showing up? Whereas range gives you an idea of spread. Highest minus lowest, 26 minus 4, 22. Interquartile range is a bit harder. This is finding the middle of the, you have to find the interquartile range, you have to find the upper quartile and the lower quartile. The upper quartile is the middle of the top, and the lower quartile is the middle of the bottom. We're actually going to do a bit of an example with interquartile range in this lesson, so I'm not going to do it here. If you don't remember what interquartile range is, though, we are going to cover it again. Really quickly, I think something popped up in chat. No, nothing new in chat. Fine. How to construct a box plot. So a box plot is another way that we can use to look at data. Box plots are what we would refer to as almost like a little bit like, in my personal opinion, it's a little bit like meta-analysis. And some of you guys I can actually use that word nowadays because like it's become a little bit more popular, and I think people sort of understand some of you guys may understand what the word meta means. So what does if you don't know what the word meta means, is meta means going outside of something or looking at it from a higher perspective. So meta-analysis is not looking at the numbers, you're looking at the information about the numbers. So it's like taking like 2 steps back. It's like kind of, you know, a dream within a dream kind of business. So meta-analysis, and that's what a box plot is that you're not looking at the numbers, you're actually looking at how does the mean and the median, and how does the range, how do these all look? What is the range of the data? How does that compare to the median of the data and stuff like that? So it's like looking at the information about the information. So that's why I refer to it as a meta-analysis. But yeah, it's kind of, that's what box plots are, is they're just information about information. And they allow us to reduce a lot of complex ideas into a very simple picture. And I think that's really, really useful, because that's ultimately what all of statistics and graphing stuff is about, is trying to get a complex idea and turn it into a picture. So that's why it's a pretty important skill to have. So let's jump in and let's have a look at what a box plot is, and then how to make one. So a box plot is a visual way of a visual representation of a 5-number summary. The 5 numbers a box plot show are the minimum, the lower quartile, the median, the upper quartile, and the maximum. So this is why I said, don't worry, we're going to look at the upper and lower quartile in a sec. So those are the different parts. Now, one of the things that I noticed after teaching this last year is that I had a lot of problems with questions, because it's like one of the questions that I got a lot was like, we tend not to use these words lower quartile, median, and upper quartile, just because there are a lot of text for each of those. So what we do is we use the values Q1, Q2, and Q3. Lower quartile being Q1, the first quarter. Median being Q2, the second quarter, because 2 over 4 is equal to a half, and that's what the median is half of the data. And the upper quartile being the third quarter, or 3/4 of the data. Obviously, maximum is, we're not going to write 4 quarters, but yeah, that's sort of what that would mean, and minimum being 0 quarters. But yeah, the idea is that's what Q1, Q2, and Q3 means. And that's also why there's no Q4, is because that's the maximum. So it's a visual way of plotting this information. It usually does it in a way called the it's called a box and whisker plot as well. I'm going to show you why it's called a box and whisker plot in a second. I'm just going to have a sip of my coffee, and then I'm going to change the slide. Now, this is often called the 5-number summary. And yeah, a lot of the time, that's what it gets referred to as. The reason it's called the 5 numbers is because it's out of 5 numbers. Now, it's important to remember that this is what the 5-number summary is, because sometimes you might think, oh, does the 5-number summary include the mean? It's like, no, it doesn't. It doesn't include the mean or the mode or the range. The 5-number summary just includes these important factors. So the first thing we're going to do is we're going to look at sizes. Now, the sizes of this is actually relatively important. The median, the minimum to the first quarter is 25%. The first quarter to the median is 25%. The median to the Q3, or the upper quartile, is 25%, and to the maximum is 25%. If I draw this as a box plot, it would look like this. So it's 25% here, 25% here, 25% here, and 25% here. Minimum, maximum, median, upper quartile, lower quartile. Now, it does seem a bit obvious, right? That, maybe it doesn't, so I really need to stop saying that. But like, yeah. If you go 25 plus 25, that means that below the median represents 50%. And if you look 25 plus 25, means above the median is 50%. Now, if you think about the upper quartile splits the top half in two, which is why there is 25% between the median and the upper quartile, and 25% between the upper quartile and the max. Same with the lower quartile, it splits the 50% into two, which is why there's 25% between the lower and the upper, 25% here. Now this idea, although it's simple to understand now, especially when I've got all these numbers written down, it is an idea that I find some students get, like, the reason I put it here is because I didn't teach this last year. And I found a lot of students just couldn't do this question in the exam or the test. Like, I don't know. It's like, how am I supposed to know that? You are supposed to know that because you're supposed to be able to go, oh, well, I can do this. And so if anyone, if you ever, you can actually think about this. If you hear that the median house price is $900,000, that means 50% of the houses are more than 900,000 and 50% are less. If the median of the test is 60%, that means half the class got more than 60% and half the class got less than 60%. If you know the upper quartile, if you know the lower quartile is 30%, then you know that 75% of the class, right? Let's just say that, let's just say that the Q1, the lower quartile was 30 out of, we'll go with 49, some random number. Then you know that 75% of the class got more than that value. So it's just, here's a question down the bottom that I wanted to do with you guys. The median of a set of data is 210. The lower quartile is 150, and the upper quartile is 260. What percentage of values are more than 150? Well, let's just quickly, we could do this in a couple of ways, but we can, let's just do, I'm trying to think of the best way to do it. I'm just going to do it like this. So we've got our lower quartile, which is 150. We've got our median, which is 210. We've got our maximum, which is 260. And then we've got some minimum and maximum number that we don't know. It says what percentage of values are more than 150? So it says if I've got 150 here, how many of them are, what percentage of them are more than that? Well, let's count. There's 25% here, 25% here, and there's 25% here. So what percentage of values are more than 150? 75% of values are more than 150. So a large amount, about 75% of them are more than 150. And that's how you can use these sort of ideas of Q1, Q2, and Q3 to your advantage. I'm going to leave this up for a fraction of a second before I change the slide. Okay. Any questions about this? Any queries? We all good? Oh man, I hate looking at this and going, look at that. Capital M, capital M, capital M. Someone is asking a question, but I have not figured it out yet. No, sir, we're all good. All right, beautiful. All right, let's keep going then. Because we've got a couple of slides to get through. We're going to create, yeah. And if we don't get through all of this today, that's fine. We can do it some later. Let's create our first box plot. Use the following data to create a box plot. I thought this would be good to do at the start. Let's just do a basic example. Here is the data that we need. Got a minimum of 2, maximum of 30, and then yeah. So how are we going to do this? We're going to do this like so. Okay, I'm going to draw a line. And I'm going to draw this line, for me, because I've got a lot of space here, I'm actually going to draw a line that's going to be 20 centimeters long. Okay, maybe a little more than 20, but that's fine. Oops, never mind. And so what we're going to do is I'm going to write, and I'm going to do on this, I'm going to mark every centimeter, but you guys can do, if you guys don't want to do a 20 centimeter line, you can do a 10 centimeter line and achieve the same sort of thing. Maybe you could go with something smaller, but yeah, I've just got a lot of space, so I can do that. And I'm going to go to 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Now, you might say to me, why the heck did I go all the way up to 40 when it stops at 30? I like to go past the maximum just a little bit. I probably shouldn't have gone all the way up to 40. I probably should have done this in groups of 5, 10, 15, 20, 25, 30, 35. Then I would only need to use 7 centimeters. So if I'm with you guys, that's what I would do. But yeah, and yeah, I would like you to draw this down as we go. The question here, 40 is excessive. Okay, yeah, someone said that. Yeah, 40 is a bit excessive. It is a bit large. So now let's put in, how do I go about drawing a box plot? What I usually do is I draw 5 lines. Okay, so how do I, the first line I'm going to draw is at 2. Oops, 2. The 2 is here. Then I draw a line at 12. 12 is here. Then I draw a line at 18. 18 is here. Then I draw a line here at 24, 20, 22, 24. And then I draw one more line at 30, which is 24, 26, 28, 30 here. And I've got 5 lines. Then I'm going to take this line, and I connect them like so. And then I take the end 2 lines and connect it like so. Then I take the tops of these lines and the bottoms of these lines, and I've got myself a box plot. Now, the interesting thing here is, yeah, you can start to sort of get an idea, and we're going to explore this a lot more probably next week and on Friday, but we could start to get an idea of some interesting things going on here. Isn't it interesting that there is a lot of values, like 25% of the values occur between 24 and 30, which is a very, very small amount. But a lot of but not many values, 25% of the values occur are spread out between 2 and 12. So it's a bit more spread out down that end than it is down this end. You can actually start to use this to get an idea of, well, if it's a lot more spread out, then you might look like that. Whereas if it's a lot more compressed, it might look like that. And you can actually start to get an idea of how this might be skewed. but we're going to talk about like skewing of box plots and stuff later on. But I'm just trying to get you guys to sort of look at these a little bit critically. These look about the same, so these look pretty symmetrical, but it's interesting to see how this section here is a lot smaller than that section. Right, I know that you guys are doing this as I'm doing it, so I'm going to give you guys maybe, I don't know, say about maybe 2 minutes to finish this off, unless you guys are all finished, in which case I can move on straight away. But let me know in chat if you want me to move on straight away, or if you need a little bit more time to finish it off. As I said, I would, maybe a nice, if you were doing this in real life, which you guys are in real life, I'd be doing like a 7 centimeter one. Oops. There's 7 centimeters. That's 7 centimeters on my screen. That's a bit better. So yeah, up to you. Same graph, just plotted a little bit differently. So someone asked, can't we just make it up not to scale but have distributed lines? Make it not up to scale. You should make it up to scale. The reason why you want to make it up to scale is because of this fact here. If I draw a distribution and I keep it to scale, and then I find out that it looks like this, I can tell from this graph that this is actually I can tell from this graph here that this is positively skewed. Positively skewed. And I can tell it's positively skewed because the minimum, lower quartile, and median are very close together, but the upper quartile and maximum are really far away from those 3 numbers. So therefore, that means this data is going to look like this. Now, if you just go, oh, I'm not going to do these to scale, and if you just do it like this, and then you then say, oh, well, we're just going to put these numbers here, 2, 12, 18, 24, 30. Yeah, sure, it looks like it's close to a box plot, but because of the scale, you won't be able to get this information here. And that information is going to be important for us later on. Now, I'm going to move on now to talk about outliers. An outlier, an outlier is, this is going to be a calculation that we're going to have to learn how to do. An outlier is a data value that is a lot smaller or higher than the other values in the set. An outlier can be detected if it is 1.5 times the IQR larger than the upper quartile, or 1.5 times the IQR smaller than the lower quartile. We call this the upper and lower fence. Now, so let's talk about an outlier first. An outlier is just a number that's just way too large. So if you're measuring, if you remember before when we were talking about test results, we said that most of them were 90%, 89%, 85%, and then some students scored 2% on the test. That 2% is an outlier. It is much, much smaller than the other values. It is like, it doesn't belong. It sort of, doesn't fit in. And if you have the other way, remember the house prices where we had one of them was 10 million, that is an outlier. It's much larger than all the other numbers. And so what we want to try to do when we look at statistics is we want to try and ignore outliers. If you've got a number that's super huge, it's probably, you know, maybe it's a mistake. Maybe if you are asked to measure the height of, you know, preps, and you get like, you know, 1.2 meters, 1.19 meters, and then one of them comes out to be, you know, 2.4 meters. It's like, well, maybe you made a mistake in your recording, and so therefore maybe that number should be ignored as an outlier. If you looked at like people that how much fast food they eat, and someone eats fast food every day of the week, well, that's not a normal thing, so it's probably an outlier. But we need a way to justify what an outlier is. What we do to justify an outlier is we say, well, if it is so large that it's 1.5 times the interquartile range, bigger than the upper quartile, then that's way too large. And so that's our measuring stick. That's what we use. We could have chosen like one IQR larger than the upper quartile range. We could have chosen 2 times the interquartile range larger than the maximum. We could have chosen 1.5 times the IQR larger than the median. But this is just a random value that, not random, but this is the value that we've chosen. Okay, so if you're looking at that, it's like, well, how did they figure that out? Like that, they've just chosen it because it's a good way to measure. If something's bigger than that, it must be really big. So we call these values the upper and lower fence, and anything beyond those values are known as outliers. I'm going to show you guys how to deal with outliers now. Let's start by first calculating the upper and lower fence. Let's take the same, no, this is not the same. Let's find the upper and lower fence of this data. So to do that, we need to do a couple of steps. The first step we need to find the interquartile range. The interquartile range is the upper quartile minus the lower quartile, or in this case, Q3 minus Q1, which is 48 minus 30. And when you do 48 minus 30, you're going to get yourself 18. So that's the interquartile range. This is why I didn't want to cover the interquartile range earlier in the lesson, because I'm like, well, we're going to talk about it later on anyway. But if you recall, to find the upper and lower fence, we don't need the interquartile range. We need 1.5 times the interquartile range. So I'm actually going to do that at the bottom here. 1.5 times the interquartile range is equal to 1.5 times 18. 1.5 times 18 is equal to 27, I think, unless I made a mistake. I may have made a mistake. Let me just double check. I think it's this. If I'm right, I'm going to be happy. I'm right, I'm happy. So it is 27. Now that we've got that, we can take that information and do 2 different measurements. The first is going to be called the upper. The first one we're going to do is we're going to find the lower fence. So the lower fence is going to be, in this case, the lower fence is going to equal the Q1, or the lower quartile, minus 1.5 times the interquartile range, which is going to be 30 minus 27. Because 1.5 times I times that, we've already done that. We don't need to do it again. So the lower fence is going to be at 3. Let's look at the upper fence. The upper fence, we can find that by taking Q1 and adding 1. No, sorry, not Q1, Q3. We're going to take the upper value, we're going to add 1.5 times the IQR, which is 48 plus 27. 48 plus 27 comes out to be 75. And that's how we find the upper and lower fence. And let's go have a quick look at this information here. 72 is lower than 75. So it's actually, that's actually fine. It's like there are no outliers at the top of our range, which is good. But if you look at the minimum is 2, but our lower fence is 3. That means that 2 is an outlier. It's too small to be in our set. So we would actually plot that differently on the graph. We would actually not plot that 2. We would plot the next value up from that 2. And that's how we would use it. And so the upper and lower fence help us find where the values which values are outliers. Essentially, all values should be above 3 and below 75. If it's a number lower than 3 or higher than 75, then that means it's broken. You guys are going to have to learn how to calculate this stuff. This is probably the most complicated thing you need to learn how to do when it comes to univariate data, because it requires the most steps. But it is still worth, and that's therefore it's worth the most marks. If we grab a look at the steps here, we've got one step is calculating the interquartile range. We've got a second step calculating 1.5. We've got a third and a fourth step to find the upper and lower fence, and then we've got a fifth step, which is actually finding the outliers. 5 steps. So these mark questions are usually out of 6 marks or something. So learning how to do it is probably pretty important for you guys to be able to get like a lot of marks. And so what we're going to do now as a final thing, and this is going to be before we wrap up pretty much for the end of the day, is we're going to do a big one. And then I'm going to get you guys to start working on 2H. We're going to look at this monster set of data. We're going to create a box plot from start to finish. Okay, and then what we're going to do is we're going to create a box plot from start to finish. Now, if you guys want to jot down all of these numbers, be my guest. It is a lot of numbers, so that might be a time. You may want to leave a gap, or you could just write down the working out that I do. So, and that's another option you guys can do. But yeah, we're going to take a stab at this and we're going to make our way through it. Now, the first thing we need to do to create a box plot is we need to get our 5-number summary. We need to get a minimum, lower quartile, median, upper quartile, and our maximum. We need to get these values. So some of these values, and this is an ordered data set, because if I was to make this unordered, it would be even harder to do. You could also get this information in the form of a stem and leaf plot, and that would be even easier to understand, but at the moment we're just going to deal with it like as it is. So the minimum value and the maximum, they're the easy ones to pull out. The minimum is 2, the maximum is 284. These might change depending on like these might change depending on if we find an outlier. The next thing we want to do is we want to find our median. So our median, well, we've got, how many numbers have we got? We've got 3 rows of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Of 11. Let me double check that. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 33 numbers, right? So 33 plus 1 divided by 2 is 34 divided by 2, which is 17. We're looking for the 17th number. So let's do that. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So that becomes our median. I'm actually going to double check this. And how I'm going to check this is I'm actually going to count from the other direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So you can actually count from both directions. It's a good way to double check if you've accidentally, miscounted. Now, the next thing we're going to do is we're going to calculate our lower quartile. Now our lower quartile is finding half of the lower half. So to do that, what we're going to do is we're going to say, well, if we've got, and we're obviously not going to include 71 because that's in the median. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've got 16 numbers. So 16 plus 1 equals 17. 17 divided by 2. Actually, I don't want to do this in purple. I want to do this in green. Not that it matters, but it matters to me. So 16 plus 1 divided by 2 is 17 divided by 2 equals 17 divided by 2 is going to be 8.5. So the 8.5th number. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8 here. Here is the lower quartile. The lower quartile is 24 plus 27 divided by 2, or 25, 26. 25.5 is my guess. I'm actually going to do this in the calculator because I'm going to make a mistake if I try and do this in my head. I was right, 25.5. That represents our lower quartile because it's the middle of the lower half. Now, the advantage of having the 8.5th number is I actually can do this for the upper quartile as well. Let me show you. We go 1, 2, 3, 4, 5, 6, 7, 8 here. You can count it backwards as well. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Halfway, yep. So we've got 108 plus 114 divided by 2. $111. And that gives us our 5-number summary. Now that puts us pretty far along in our calculations. Now, before we can start plotting this out and getting a nice little graph, let's check for outliers. Because we want to, because this 2 seems pretty small, and this 284 seems pretty large. So let's check for outliers. How do we check for outliers? Well, we're going to find the interquartile range. The interquartile range is Q3 minus Q1, which in this case is 111 minus 25.5. 111 minus 25.5 equals 85.5. That's our interquartile range. Beautiful. We don't want the interquartile range. We want 1.5 times the interquartile range, which is going to be 1.5 times 85.5 equals 128.25. Now, ladies and gents, if you've got any questions as I'm going, let me know, because I'm just going to keep powering through. I'm like not stopping here and being like, does everyone understand? I'm just going to keep trying to get this, because it's such a long question. I'm just trying to do this. So now what we're going to do, so just interrupt me. You can even use voice chat. You are allowed to, Sir, stop. Why did you do 1.5? So now what we're going to do is we're going to find the lower fence. Now what I'm going to do is I'm going to get rid of some of this extra data here. The lower fence is found by taking the Q1, or the lower quartile, minus 1.5 times the interquartile range. And that's going to be 25.5 minus 128.5. 25.5 minus 128.25 is negative 102. Well, that's a lot smaller than, that's pretty far down. So that means we've got no negative, we've got no outliers smaller than the low. Yeah, that fence is really far down. Okay. If this, and yeah, because it's negative, straight away I can pretty much say, yeah, don't worry about it. If it was like, if the lower fence was like 5, then I would be like, this is an outlier. Let's have a look at the upper fence now. The upper fence is the same game, but instead it is Q3 plus 1.5 times the interquartile range. Q3 in this case was 111 plus 128.25. 111 plus 128.25 gives us 239.25. Now, if we look here, there is a number that is larger than 239.25. It is our maximum at 284. This is a lot larger than 239. This is an outlier. So I'm going to change our maximum to 236. Now, because that's below the upper fence. Now, remember I said, heads up, guys, that number may change. And that's because, yeah, if it was like, if the upper fence was even less, if the upper fence was 230, then that would make 181 be our maximum. But yeah, in that case, 284 is our outlier. Now that doesn't mean we can like ignore it completely. It just means it's an outlier. Now that we've checked for outliers, we've done everything we need to actually plot the box plot. So what's our box plot going to look like? in this case, we're going to go, let's see, we've got, if I go up by 50s, then it's going to be 5 centimeters long. If I go up by 20s, it's going to be 11 centimeters. But I still need to go up to 284. All right, looks like, let's, if I go up by 25s, I need to get to about 300. So if I go up by 25s, then it's going to be 25, it's going to be 12 centimeters long. This is just the maths that I'm doing in my head because 12 centimeters, yeah, that'll do. I'm going to do that. I'm going to do 12 centimeters long. And then I'm going to do 4, 6, 8, 10, 12. And then I'm going to do this. I'm going to go 0, 50, 100, 150, 200, 250, 300. Now, okay, so our minimum is 2. So that's easy to draw. I can just draw a line here at 2. It's going to be really close to the 0 line. So I'm pretty much just going to do it just a smidgen away from the 0 line. But yeah, it's 2 because it's be difficult to tell. I'm actually going to write the number 2 above it just so that you can tell. The next is 25.5. So it's pretty much smack bang in the middle, which is nice, of between 0 and 50. Okay, cool. The next one is 71. That's our median. So 71 is close to the middle of between 50 and 100. So I'm going to do about there. The Q3 is 111. So it's pretty, that's a lot more closer to 110. So it's probably about a fifth of the way between, it is about a fifth of the way between 100 and 150. So I'm going to do it about there. And our maximum is 236. It's going to be pretty much a little bit closer to 250 than 200, but yeah, it's about here. Have I missed one? Oh, for some reason I missed the first quarter, 25.5. For some reason I didn't draw the line there. All right, so now I join the middles of the outer ones, and then I join the tops of the inner ones, and that gives me a box plot. Now I have to, and that's pretty much it. You can actually tell here that it's got a really long tail. It's got a, whisker. This is really long. You look at that, whereas this one's quite short. So most of our values occur below 111. 75% of our numbers occur below 111. So yeah. Now, I can't ignore this outlier completely. So what I need to do is I need to mark that outlier on this graph. How I do that is like this. I go to 284, which is going to be about here, and I draw a circle. Or sometimes you just do a point. And I'm going to write 284 here. If you have more than one outlier, then you would draw, and if you have outliers in the negative, then you would draw other dots. But for us, we only have one outlier, so that's the only one we need to draw. The reason we draw this outlier is because we want people to understand is that there is a number larger than 236, but it is so large that it's an outlier, and that's why I've included it in this picture. And that's how you would draw, and if you have more than one outlier, you just do more than one dot. But that is the full method on how to draw a box plot from start to finish. What you guys should have seen as I went through this lesson is that I built up to this point. Okay, I tried to build up to this point as we went. So, for example, finding the drawing the box plot. I already discussed this, but we discussed it when we already had Q1, Q2, Q3, and minimum maximum. Finding the upper and lower fence. I already discussed that. You know, when we, talked about what an outlier is. And identifying what outliers are. I've already done how to find the median and the lower and upper quartile from a list of numbers last term, but I already did this, at least this morning I already talked about how to find the median of the set data. So all I did in this question was combine all of those skills together. And that's why this question is worth usually probably a lot of marks, because you're combining multiple skills together. Now, you guys are going to need a fair bit of practice on this. So what you guys are going to be asked to do now is to work on 2H. I'm going to ask you to do all of the questions in 2H. And yes, it's going to take you guys a while, but if we don't have class tomorrow, then that's what you would be expected. Even if we did have class tomorrow, it's probably what we would be doing in class, is working in 2H.